The boundedness property then, f is continuous on this interval, f is bounded on AB, we've proved that, and f attains both a maximum value, which we've proved, and now we're going to prove the minimum value somewhere on AB. So we need to show that f attains a minimum value somewhere on AB. So here's the proof then. It's in the exercise section. So let A be this set of all the f of x's between where x varies from A to B. F is bounded on AB, as we said before, didn't we, by part 1. So if that's the case then, that f is bounded on AB, then the set A is bounded both above and below, isn't it? A is bounded both above and below. So we said let's let M be the inf, we've done that before, and capital M be the sub. What is now required is to show that M and M are both values of the function f. So we've shown that one of them was. To this end, suppose by way of contradiction, so we're going to look at the other one now, that there is no value of x for which f of x equals lowercase m. So that's what we're going to look at now. Let's define this new function as before, for all x in AB. By the same reasoning as before, all these constituent parts are continuous. So by the sum product and reciprocal and quotient rules for continuous functions, g of x is continuous. It's well defined because this is non-zero, because f of x does not equal m, and so this will not be non-zero. So it's well defined and it's continuous. So by part 1 then, if it's continuous and well defined, g must also be bounded on AB. And so there exists a real number k dash then, positive, such that gx is less than or equal to k dashed for all x in AB, because it's bounded, so we can say that, can't we? That's fine. So we're going to use that property here. So g of x is less than or equal to k dashed, because g is bounded on AB. And k dashed is positive, so what does that mean then? Well, replace this by the value of g of x here. We've got this inequality. We can then move the k dash down because it's positive, and we can move the fx minus m up. Now fx minus m is the infimum, so f of x will always be bigger than or equal to this. It doesn't equal it, so this is always positive. So this can be moved up to the top, and the inequality is preserved. And then we can move the m over, and we see that f of x, reading from right to left, is bigger than or equal to m plus 1 over k dashed. So that tells us then that 1 over k dashed m plus that value is a lower bound for the set of f of x's, because we've got all x in AB. So this is a lower bound, but the trouble is it's bigger, because this is positive, this is bigger than the greatest lower bound, which is m. So this is a contradiction. It contradicts the fact that m is the greatest lower bound for f on AB. So the assumption must be wrong that we assumed at the outset must be wrong, so there must be a value of x such that f of x equals m. So f does attain a minimum then, somewhere on AB. And that concludes the proof for the particular theorem.